introducing everybody today. I was also told I need to, unfortunately, reduce some safety briefing, so I'll quickly go through this. So in case of an emergency alarm, please remain calm, follow the exit sign, the little green sign, and go outside. There is an assembly point. You'll be safe there. Inform anybody if you see a missing person, and follow instruction from the emergency controller. I think that should cover everything. Also, do not touch the meteorite. Maybe, who knows, you might get superpowers or an alien virus, something like that. All right, so we're all here today, as you all know, thanks to following the event of the 25th of August, where Eyewitness all along the garden route saw light in the sky, heard explosion, and basically showing that a meteorite was falling on the Eastern Cape, and fragments fell all the way from, I think, the Hunters Valley, all the way to Ado Park, etc. And in one farm near Kirkwood, around 9 a.m. on the 25th, a little girl heard a noise, heard something fall on the ground, and decided to go investigate, which is probably the first sign of a future great scientist. And then the family contacted Dr. Caladot from the geoscience department, which went there and collected the sample, but she'll tell that story in a lot more detail than me. So this is a great opportunity for research and collaboration between university, Nelson Mandela, Rhodes University, and WITS. And the study of meteorite can bring a lot of information about the origin of our solar system, how a planet forms, and a lot of things like this, and maybe even more. So today we host a few distinguished meteorite experts. Professor Roger Gibson from Wits University, who is a world-renowned expert on meteorite. He is especially impact crater all around Africa, such as the Rutherford impact crater south of Johannesburg. He's worked all his career on various meteorite sites around Africa, Madagascar, etc. Dr. Dion van Niekerk from Rhodes University, who is an expert of electron microscopy and the very fine study of minerals and their chemical composition, and he has worked on meteorite before and what their chemistry can tell us about our solar system. Dr. Leo Bonapartis, who is also from WITS, a mineralogist and also an expert on meteorite, and our very own Carla Dodd, who was a long-time student in our department, became a doctor, and now is a staff member. We're all very proud of her, who is maybe not a meteorite expert, but an expert on microbial life, and who knows, she's actually an expert on microbial life and how it leaves evidence in rocks. So who knows, she might see something like that in a meteorite and be on the way for a Nobel Prize. So that's all I had to say today. I'll leave the floor to Professor Zeni, who will introduce the speakers. Thank you.
Thank you, Nicholas, and perhaps thanks to Prem and colleagues from Comms and Marketing for putting together such an event so quickly, which is a collaborative effort between Mandela University, Rhodes University, and University of Witwatersrand. So, and we are here now, and the small task for me is to welcome everybody to this unveiling of the meteorite that fell on Sunday 25th. And of course, the briefing that will be done by scientists on this particular fall event. So special welcome to the scientists, as mentioned, Professor Roger Gibson from WITS, Dr. Dion van Niekerk, also from WITS, and Dr. Leo Bonapartis from Rhodes, and of course our own Carla Dodd here. We also have Slindokuhle Mavuso from the Eastern Cape Heritage Resources Authority. So welcome, sir, and welcome to the colleagues as well from other universities. And of course, welcome to the public as well, and to universities who are represented here. I see a lot of purple from Rhodes, which is pretty good. I used to work there for about 8 years or so. So it's good to see Rhodians here. And of course, we have other scientists who are interested in this particular event also. We also have some young people in the room. I see some young kids, so it would have been actually good to see more school children, but I do see a couple in the room, so welcome. And welcome to members of the regional, national, and international media who are here and those who are online. So, of course, Nicholas has already mentioned, some of us learned about this special event on social media mostly. And observers were saying all sorts of things. There was a lot of speculation. Some said this looks like re-entry of space junk from a satellite somewhere. And some saying it's not as fast as meteors, you know. And of course, we can all guess which name comes up the most on social media when it comes to space junk and satellites. But I think the community needs to let Elon Musk do his good work. Scientists are going to tell us what this is all about. All of that will be demystified. So obviously myself, I was very excited, you know. I was interacting with Dr. Kaladord on email saying, you got to do this analysis, this analysis, this analysis, only to learn that a sample of this nature is a heritage resource, and there are certain things that you cannot do without certain permissions. So it was good to learn that. And of course, maybe Slindokuhle Mavuso will teach us a little bit about that. Right, so obviously we are to learn a lot from this kind of sample, you know. We are interested to learn about the kinds of messages such rocks carry from the past in terms of beginnings of our universe, of our solar system.
We just so lucky that it landed on our backyard. So we are very appreciative as an organization, as you know, a government organization, to be part of that process and actually facilitating the research, making sure that we have the best people on the job and on working on this stuff. As scientists, we always form a lot of international teams, so we're excited to the collaborations and the stuff that it's going to bring to all the institutions involved. And yeah, we look forward to seeing the results and just kind of like what we're going to see today. Thank you.
So I'll introduce Professor Roger Gibson from Witwatersrand University, who will give a little bit of background on what meteorites are and what they tell us about the universe.
Thank you, Dr. Tenelier, and thank you to the Dean for the invitation to be here to present the results of our findings over the last week. It's incredible to think how little time has passed and how much has actually changed. And I know the team has worked very hard. We're all exhausted, but I think it's important that we get the information out and show that, and to help people understand what is there. So although each of the sections of the presentation will be given by one of us, it's really a collective effort. So everything has been processed through the team, so we are working collectively on this. And it's my duty to bookend the really important part that will be described by Dr. van Niekerk and Dr. Bonapartis, which is the meteorite itself. There are a lot of questions out there, as the Dean indicated, and so we hope that from this presentation we will help people understand what happened, how it was linked, and how these things happen and are happening continuously to us around the world. So I've got to get you a few definitions here, because we see on social media how things are bandied around and terms come out, and they can lead to confusion. So very quickly, a run-through of meteoritics definitions. An asteroid is a piece of rock in space. It's not a planet, it's a tiny piece of rock that's around there, and there are lots of them. A comet, however, is actually a body that's made up mostly of ices, of various things, not water necessarily, methane and ammonia, that come from way out in the solar system where it's very cold. And when they come into the inner solar system, getting close to the sun, those ices start to sublimate. They evaporate and create a massive tail that will stay in the night sky. If it's viewed from Earth, they could stay there for weeks or months. So these things are not coming close to Earth, actually. What we are concerned about then is what happens from the transition of an asteroid in space to when it becomes a piece of rock from that asteroid lying on the Earth's surface, which is a meteorite. And the bridge between those is globally, generally called a meteor. The meteor is an event. It's a bright streak of light that lasts for a few seconds that passes through the sky. And we can see these things in the night sky quite easily. But they're actually happening right now. And we just don't see them because the sun is up. So we're under constant bombardment from these particles. Now, to get down to the detail, what's the difference then? Why are the scientists talking about something called a bolide? And the answer simply is size. Meteors are very, very brief streaks of light. They normally last a second or less, or a couple of seconds, and they're gone. A fireball is a very bright meteor, and if you want the scientific definition, it must be brighter in the night sky than Venus, which you can see often in the night, in the early evening or dawn sky, one of our planets. A bolide is a special type of fireball which explodes somewhere along its flight and then disappears. So the indication then is that we're dealing with something that is much larger. Some debris, of course, as has been indicated, is not actually space rock. It's junk that we put up there. For instance, space rocket stages that come back in. Some people are now reclaiming those rockets and bringing them back quite gently for reuse. But in other cases, these things are left to float slowly back down to Earth. And every now and then a satellite that has reached its sell-by date, is shut down, may come back into orbit. And these things typically come in, and you can see they often come in as a much more dispersed range of fragments that slowly persist across the night sky. They're not moving as fast as the rocks, and they come in much more slowly. So these were things that people talked about in social media. What we are talking about is a process called hypervelocity bombardment. And because the speed is so incredible, cosmic speeds, everything in the universe is moving. We are moving phenomenally fast through space at the moment. And even if something was stationary in space in front of us, it would slam into us at tremendous speeds. But those objects themselves are moving. And so there are little pieces of space rock that are flying through space, and if they intersect with Earth, they literally end up something like a bug on a windshield of a car. They smash into the planet. The average speed is about 20 kilometers per second, or 72,000 kilometers an hour. And because of that, as the particles come into the atmosphere, even with the thin upper atmosphere, they start to rub against that atmosphere and cause friction. And that friction causes them to heat up, start to glow, ultimately to melt and to start to burn up. And the temperatures reached are well in excess of the melting temperature of most rocks, 1800 degrees. Most of these particles are very, very small. They're sand or pea-sized, and that's the source of meteors. They burn up very quickly in the upper atmosphere or slow down. The drag slows them down, and they drift down slowly to the surface. So you can pick up meteoroids in your gutters. Some of that fine dust that there is not coming from the ground, it's actually settling through the atmosphere all the time. But a few, every now and then, are larger. And because they are larger, they have much more momentum behind them, and they penetrate through the Earth's shield. They burn brighter and longer because they are bigger. And as they penetrate into the lower atmosphere, it becomes more dense. In other words, the landing or the process becomes much harder. It becomes much more energetic, and it's much more catastrophic. So, to wrap up this section, what then if something lands on the Earth? It's a meteorite. For most people in the public, it's a meteorite. But for scientists, meteorites are many, many different things. And each of these different types of meteorites plays a role in our understanding of the origins of our solar system, the formation of our Earth, possibly even our own origins as carbon-based life forms. So don't worry about that organogram, but it just shows you the differences. And you can see, obviously, from these different images, the different types of meteorites. Chondrites being the most common ones, and then the ions being the most dramatic, and the stony ions being the most dramatic. But we're going to spend some time talking about this rather innocuous-looking one on the left-hand side, the achondrite. It's not the meteorite that fell now, but achondrites, as you can see, form a very large group that comes down on this family tree here, and they spread out here, and they have a lot to tell us about how our solar system formed, how our Earth formed. And that is why we're particularly excited when we get an achondrite. So, why are they important? There are about 75,000 meteorites currently categorized and catalogued in the International Meteoritical Database. But actually, they would fit into 2 passenger buses. So that's not a lot. So you can understand that most of these are very, very small. Of these, chondrites make up virtually 9 out of 10 of all meteorites found. And they are actually bodies that were built out of the dust and gases from the early solar system, some of which melted to form these very characteristic little droplets called chondrules, hence the name chondrites. They are the oldest rocks in the solar system. They date almost to the formation of the sun. And some of them, particularly carbonaceous chondrites, are particularly important because we see that even in the earliest part of the solar system, carbon was part of the gas cloud that gave rise to us. And of course, we are carbon-based life forms. So particular excitement occurs when a carbonaceous chondrite is found. So where do these come from? They come from bodies that accumulated as a result of slow collision and sticking together in the earliest few tens to hundreds of millions of years of the solar system's history. How did they end up on Earth? Well, they had to have been slammed into by something else at hypervelocity that broke it into pieces. And those pieces are now debris in space that the Earth ultimately scoops up if these things pass through our path. Now, ions are the most dramatic ones and probably the easiest ones to find. They form about 6% of the total number of meteorites, but actually a staggering 84% of the mass, because they are the biggest meteorites that come through. And the ions come from the cores of bodies that didn't get broken up too early, or bodies that were bigger and were able to actually heat up from internal radioactivity in the earliest stage of the solar system. And as a result of that, once they melted completely, the heavy elements like iron and nickel gravitated towards the center of the body, and the lighter elements ended up forming silicate minerals in a mantle around that, and then in a hard crust at the edge, just like our Earth. So you can understand that ions and their achondrite shells actually tell us something about how Earth must have actually formed and developed its own core, mantle, and crust. And then some of them are actually pieces of the crusts of Mars and the Moon that have been blasted off. And these people get very excited about. So we will be talking, as you will see from Dr. Van Niekerk and Dr. Bonapartis, we'll be talking about achondrites. A relatively rare group, less than 1 in 10 will come from there, but a very diverse group. And part of our task is to find out where in that diverse group we actually have our new meteorite. So I'm going to hand over now to the next speaker, but I think Dr. Tenelier will introduce her.
All right, so now let me introduce Dr. Carla Dodd, who is the Nelson Mandela University scientist who first got hand on the meteorite. She'll tell us that story.
Hi everyone, it's really good to see you all out here. And as mentioned, I'm not a meteorite specialist. I actually work on microbialites, and I can talk about those for hours, but I only have 5 minutes to tell you more about what happened behind the scenes this past week and how we all have been working tirelessly to get some information out there and to make sure we're following protocol, collecting good and sound scientific data and communicating that to the public. So without further ado, I first want to say that we scientists are human too. I was out cycling with my mother in the Elands River Valley when this event happened, and when we heard the noise, our first reaction was like everyone else's, what was that? And we thought this could probably be some thunder. Looking up, no, the clouds don't look very promising. And my mom thought, okay, maybe it's an earth tremor. So when we got home, the first thing I did, I went to my primary news source, which is, of course, social media. And there I saw Jessica Botha's post that was made on Snow Report South Africa, and a friend forwarded Zoe van der Merwe's video of the Bolide flight. And after that, a member of the Astronomical Society of South Africa, Peter Hurst, got in contact with me, and Prof. Roger Gibson from Wits University contacted me with regards to obtaining the right permits and the way forward for this investigation. So as Prof. Roger Gibson has mentioned, not a lot of time has passed since this event has occurred, and we scientists are not very reactive creatures. We like to move slowly, and especially as geologists, we are not often in a rush, since we study rocks that have been around for millions of years. So I think it's really significant that in less than 12 hours since the bolide was sighted and the sonic boom was heard, we already had an indication that meteorite fragments were collected, and we had a semblance of a plan in place. And of course, in true South African fashion, it wasn't long before the jokes were circulating either. But we really need to give credit where credit is due. We would not be at this media release today if it wasn't for the fantastic observational skills of 4 young people and several eyewitnesses as well. So near Port St. Francis, Stephen Sharp, Zoe van der Merwe and MC Ferreira not only observed the bolide flight and heard the sonic boom, but Zoe managed to capture it all on video. Meanwhile, 9-year-old Elizé de Toy heard a noise and saw something fall from the sky in her grandparents' garden. And when she went to investigate, she saw that there were some strange-looking rocks lying on the ground. And when she took it to her mom thought, maybe this is related to Zoe's video, which she also saw on social media. So she posted the photos of the rocks to Snow Report SA, and the rest is history. Another key witness is the captain of the St. Francis Safari's boat, who witnessed the bolide event, and his story was already broadcast on the SABC News on Sunday afternoon. Initially, there was some confusion whether some fragments may have fallen in the sea, but after we verified this, it has been noted that this was in fact not the case. So the next few days were a bit of a blur. I don't think any of us have had much sleep, to be very honest. But on Monday, Jessica and Elizé delivered the samples to me at Nelson Mandela University. And I just want to pause and reiterate how significant it is that they did this. Because without those fragments, we have very little to go on. It can take ages to search, and you might not get anything from that. So I just think it's really amazing that they were willing to hand over the samples so that these can be analysed and curated for the benefit of all South Africans as well as the international community. And within 36 hours of the event, we had consensus that this was in fact a meteorite. And meanwhile, we were working on media statements, conducting radio and television interviews to ensure that there was some information going out to the public with regards to this event. The statements also explained that these rocks are protected under the South African National Heritage Resources Act, and a permit is required for collection and analysis. So Dr. Dion van Niekerk from Rhodes University was granted a permit by the Eastern Cape Provincial Heritage Resource Authority on Tuesday to collect and study any fragments related to this event. On Wednesday, the team arrived from Wits and Rhodes Universities at Nelson Mandela University, and we had a meeting with the Eastern Cape Provincial Heritage Resource Authority on the way forward with the investigation. And the rest of the day was spent describing and cataloguing the samples and setting up interviews with the eyewitnesses. On Thursday and Friday, we verified some of the eyewitness reports, specifically those that were circulated widely on media. So we met with Zoe, Stephen, and MCA in Port St. Francis, where they took us to the site where they witnessed the event. We also met with Tommy Terblanche, who was out hunting with a friend when he witnessed the bolide, and he was able to provide us with some very detailed description in terms of the direction of the flight, which was very helpful. And we spoke with the owner of the St. Francis Bay Safaris boat, who regarding the eyewitness report of the skipper. And all these reports were in consensus, and they corroborated what we heard from Elise and from Jessica. And I also want to say that we've received hundreds of reports, both from witnesses and eyewitnesses, and we thank you for all of that. It's really great to have these multiple lines of evidence pointing in the same thing. And this really helped us to define the flight path as well as the strewn field where there may be other fragments. On Thursday, we also spent some time doing field visits. So Dr. Dion van den Kerk went out with Tommy de Blanche, and we just had a bit of time to get a feel for the surrounding area, see what the land use is and the local geology, as well as to identify a few objects that may confuse citizens when they want to report findings to us. So meteorongs rather than meteorites. And these include for example, animal droppings and some local rocks. So currently we're working on getting permission from landowners where we think that there may be some fragments to obtain access to their properties, and then we will conduct systematic search parties. And that's it from my side. Thanks, everyone.
Let me welcome back Professor Gibson again, who will talk more specifically about the event of August 25th.
Okay, so that's what we were doing, but what were we collecting? And in fact, it's important to note that the role that the Astronomical Society of South Africa has played in this. I like to stay on the ground, even though sometimes I've got to look up. And the physicists and astronomers obviously spend a lot of time with the physical and mathematical calculations about orbits and what have you, and our place in space. And they are crucial here, and we are very fortunate to have Mr. Tim Cooper, who collaborates internationally with NASA and with the European Space Agency and other groups around the world in quantifying what these bolide events represent. And unfortunately, he could not be here today, but I am talking mainly on his behalf, but also on work that Dr. Finitra Adrian-Penomanana at Wits is doing with regard to the seismic data, which I will show you. So really what this presentation now does is it starts with the eyewitness accounts, and then it shows the scientific verification and the explanation for what they actually saw. So just remember, a bolide is a special type of fireball that explodes in what we call a terminal flash or terminal blast, and then often will form fragments that fall to Earth. Why does this happen? Well, the bolides are one part of a spectrum of material that comes in every day into the atmosphere. Between 100 and 200 tons of material enters the Earth's upper atmosphere every day. Most of it is this sand and pea-sized stuff that just gets burnt up in the upper atmosphere or slowly drifts down through the atmosphere as it's stopped. But then we do see bigger ones, as I said. So the atmosphere is actually a very effective shield against very small fragments. It melts them, and then the melt droplets disappear off them, which we call a process of ablation, and it slows them down with the drag. The atmosphere is up to 100 kilometers high, and so there's a lot of slowing down that can happen. But bigger rocks have more momentum. Think of Ibn Etzebeth running into you, right? You're not going to stop him. So they are the lock forwards of the meteor world. And actually, it's estimated that between 10 and 50 meteorites land on the Earth's surface every day. Unfortunately, of course, 2/3 of our surface is water, so there are a lot of them sitting at the bottom of the ocean. So we get excited about the few that might end up on land. But actually, even though we have spread over the planet, there are a lot of places that are remote and a lot of places where these things land, so they don't necessarily land near us. How big are the fragments that then fall into the so-called bolide category? Well, they'll typically be meter size, so they'll be about 3 to 5 tons. Okay? They are dense, they would therefore be heavier than your average car, but they would not be bigger. So we said a car-sized object, but actually a car-massed object or more, but it actually turns out to be more like a motorcycle in terms of its size. There are also, as I will say later on, superbolides, and these actually start to put us into the dangerous realm, and I'll just mention that. So what happens is the bolide punches, the body punches through the upper atmosphere, which is thin, and as it comes down, it's getting into denser and denser atmosphere. Anyone who's belly flopped into a swimming pool knows that even though that's water, it stings. And so what we're going to find is that the body encounters more and more resistance at that hyper speed. And so it starts to vibrate, it starts to end up with stresses within it. And if there are pre-existing fractures in the body, or fractures that are made through that process, those may open, particularly as that air that can't get out of the way starts to push its way inside the body and heats up and therefore expands. And so ultimately there is this explosion. And that is the terminal blast. And that is actually, if you follow the narrative of the Cape St. Francis group, that's what Stephen said, Stephen saw, and Zoe managed to photograph the end part of that. So let's move on to that. So Tim has taken Zoe's video and broken it up into tiny fragments so we can study each point in time. The video starts at 8:50:49 seconds local time, which is 6:50:49 seconds universal time. And it starts after the main flare, which caught Stephen's attention. So we're looking at the breakup, the end part of this phase, which lasts only 2.8 seconds. So we've missed the other part, and we're hoping that there will be videos of that. We have some from particular angles, which Tim is now processing. And so what we see in this process is a series of parts of the original body slowly drifting apart, flaring, and then going out. And that's when they slow down enough that they're no longer being heated up by friction, and they enter dark flight. So what we then did was we looked at the eyewitness reports, and people very kindly sent in very detailed reports indicating their position, which way they were looking, what they were doing. You might have missed the bolide because you were chopping up your food, but you heard the sound that came later. And we also had the evidence that said people saw something, heard something, or felt something like a ground tremor, or some combination of those. And so these have been put together, and what we find, and then of course, there was the initial TV report that came out on the Sunday news, suggesting that objects may have splashed down in Jeffreys Bay. It turns out to be a bit of miscommunication, and so that was not what the eyewitness saw, and so it's helped us. We've received over 150 reports, and it's growing every day, and keep them coming. We would like to see what people have to say. The furthest sightings are over 600 kilometers to the north on a car at Petersburg, and 650 kilometers to the west, someone climbing a mountain in Ceres in the Western Cape. And when we start to put it all together, the external viewings are all sightings of the bolide, the bright light. But as we get closer to Gqeberha and west towards George, we find that there's sightings, but there's also sound, loud sound noises, sonic booms in the air, and violent vibrations, or moderately violent vibrations. People could feel the ground trembling. And so from that, we conclude that the focus of the event was in this region between Gqeberha and George, and that the body, from the eyewitness accounts, was moving towards the east-northeast or northeast from essentially the coastline, moving inland. And we'll see in a moment that the main mass detonated. This is fixed by NASA and programs, and international programs, the main mass detonated over the Great Windhoek Mountains that are west-northwest of Gqeberha. The last thing I want to do is point out this point up here, Boshoff. It's not a viewing point, but I want you to mark that line, because at Boshoff we have an infrasound station, one of the 60 around the world, that monitors the movement of high-speed objects into the upper atmosphere. And it's primarily part of the Cold War defense strategy and monitoring strategy to look for missiles coming through the upper atmosphere. But thankfully, it's never been need to be used for that, and it has been turned to study of these bolides coming in. So remember that infrasound would be a sound that is lower than the human hearing threshold, and it can travel great distances, so it's very useful. So elephants use it to communicate, for instance. Our station, I47ZA, is near Kimberley at Boshoff, and it's just under 600 kilometers from Gqeberha. And what we see at the station, here is the station record with the time indicated based on universal time, which is 2 hours behind us. And you notice that it's all okay until this point over here at 7:22 or 9:22 local time. So isn't that a bit late? Well, the problem is you've got to remember that sound does not travel as fast as light. Sound is going to take time. This is how we work out how close we are to a lightning strike. We time the distance between the strike, the light, and the sound that is caused by that violent strike. And so it takes 29 minutes for sound to travel roughly 590, 600 kilometers at 1/3 of a kilometer per second. And so if we back calculate that, we see that in fact it fits an event at roughly 8:53 local time. Remember Zoe's video, roughly 8:51. So give or take a little bit of variation in the sound. It's got 29 minutes to mess with the atmosphere. We're on track. And what is even more important is that when you plot, because the station actually works out the direction from which that sound came, the cluster of readings all sits in the direction. Remember, this is the direction towards Gqeberha and the area to the west. So it sits in that vector between 176 and 199 degrees, which is essentially south to south-southwest. So the infrasound station locally was able to confirm there was this massive event, if we ever had any doubt, and to indicate what was there. But can we go better? And here we turn to an organization called the Center for Near-Earth Object Studies, CNEOS, that reports. It took 2 days for it to finalize its report, and it came up with a table. You can see the table along the bottom. It gives the coordinates, and then it tells us some of the details. And it worked out that that object was traveling at this cosmic velocity of 20 kilometers per second. The energy release was equivalent to 92 tons of TNT. So if you find an average-sized room of 4 by 4 by 4 meters, I know our ceilings aren't 4 meters high, but this one's probably 4 meters high, you would pile that into place, and that's how much energy was released by this event. The disruption occurred quite high, at 38 kilometers altitude. So what people were seeing for a brief moment, I know we see stars, but on a brief moment you were seeing up to 80 kilometers to 40 kilometers above the land surface, not just behind the clouds, a long, long way up. This was the 20th bolide reported on the site in 2024. And its diameter, as I said, we thought car size. We were having a look at the images, and it was a thumb suck at that point. But it'll be slightly smaller than that, less than 1.5 meters, probably about 1 meter cubed, so about this size. And there it sits. It is on the database. You can look it up. There's the little dot sitting there off Gqeberha. So what else do we have? Well, actually, there are seismic stations that are monitored by the Council for Geoscience all over South Africa. And there are some to the west of Gqeberha. And here's the station Eyewitness, which lies about 100 kilometers to the west of the city. And what we see happening there is that again, at universal coordinated time, we have an event just before what would be 8:55 a.m. our time. There it is, that very sharp spike, and a lot of activity just immediately after that. So the station is shaking. There's a tremor. That tremor has multiple sources. Initially, what is happening is because this object is traveling much faster than the speed of sound, it creates what we call a Mach cone. You know about Mach 1, Mach 2. And this is called breaking the sound barrier. So direct sound waves hit the station from the air. And that's what probably gives this sharp bounce. In addition, the explosion, the terminal blast at 38 kilometers would have radiated out a massive explosion that could then have been picked up by the station. And finally, some of those sonic waves hit the ground, causing them to vibrate, and the vibrations travel along the ground to the sensors. So we have all of this here. We notice that the event happens at the station at roughly 2 minutes after what was recorded on Zoe's video. And so we can estimate that it was about 40 kilometers from the station, which is remarkably similar to the detonation height of 38 kilometers, suggesting that the bolide probably passed very close to the Esville station. And so to conclude then, the local and international sensor instruments that are highly sensitive have corroborated each other and the eyewitness accounts that the sonic booms and the sounds like thunder that people heard, the ground tremors that they felt, even though they are delayed, can be explained as a result of this high altitude bolide. And what we're seeing is proof that the bolide was actually very high in the atmosphere, meaning that the sound energy had to take a long time to get to the ground, whereas the light energy was essentially instantaneous. So it now gives me pleasure. That's the background. Now we get to the real part that people are here, and Nicholas will introduce these.
Hi, let me introduce Dr. Dion van Niekerk from Rhodes University, who is going to share with us some of these initial observations on the sample that were found last week. Thanks, Nicholas.
Where are we? Good morning. How do I forward this? I'll tease you a little bit first. You know, it takes a special person to study rocks. Geologists are frequently at the brunt of jokes. But, you know, if you consider that meteorites are the only physical pieces of the world beyond our atmosphere, of the universe, that we can actually hold and touch, you know, it's really cool being able to study these rocks. So they might look boring, but it's very exciting. The point I want to bring home on this slide is that these are some of the fragments of the meteorites. There are 5 fragments in total. The meteorite broke up when it hit the ground. There are 2. These 2 are the same on the left and right at the top. Those are part of the same fragment, and the 2 at the bottom. So we're looking at 1 fragment at the top and 1 fragment at the bottom, just to give you a sense of scale and how big they are. They are small, actually, you know. It's 90 grams total mass. This top one, you can see it's 4 centimeters. This bottom one's about 3 centimeters. And as Professor Gibson was saying, you know, we're looking at a much smaller than car-sized. So it is incredible that somebody actually was at the location where these rocks fell. You know, there might be more rocks out there that we're going to look for, but it really is a needle in a haystack. You know, there isn't a lot of this material that reaches us, and it's an incredible contribution to science. So this is a close-up of one of the fragments I showed previously. I'm pointing out the fusion crust here. So you'll see it's black. Dr. Dodd was referring to the meteorongs, and she showed a slide of some of the animal scat and a rock with a black crust on it, a patina. And this is why people can confuse real meteorites with false meteorites or other rocks and things. When we look for meteorites, we commonly look for this fusion crust. This is basically a molten outer portion of the rock. As it's coming through the atmosphere, it's heating up, it's melting, and then it cools quickly and it forms this black crust. So this is a cue to us when we're looking for meteorites that we should be paying attention to whatever rock is lying around. This is the other fragment, and what I'm pointing out here is you can see there is also fusion crust here, but here we actually see an interior part of the meteorite where it broke open. So if this side was facing up, you wouldn't necessarily recognize this as a meteorite, but because it's got that fusion crust on it, you would recognize that. So getting into some of the nitty-gritty here, I have to stress that these are preliminary observations. You know, we've had these rocks for only a few days, and so usually when we start describing them, we give it a fancy term. We say we're describing them macroscopically, which basically means we're eyeballing them. You know, this is the first start to any scientific investigation. It's just to get an initial idea of what we're working with and to plan our more detailed analyses from there. So what we can tell here, observation-wise, is importantly that there are no chondritic textures. So Professor Gibson was referring earlier to chondrite meteorites, which dominate the meteorite collections. And it's important to note that there are no chondrials or chondritic textures or anything associated with chondrites visible in these rocks macroscopically. So from that, we can immediately say that we think we're looking at an achondrite. There's also no metal. You get a lot of iron meteorites or stony iron meteorites that contain metal. There's no metal in this. You can observe a light gray matrix here. This is really microscopic, so we'll have to look at that closer later on, as one of my colleagues will explain later on. But this is a bit of a brecciated texture because you've got that fine-grained matrix and then you've got these clasts, big clasts of different sizes in there. And we're not sure at this point what it is. We really have to look at that under a microscope. These could be pieces of other rock fragments from the parent body of the asteroid, for example. Importantly, we can see some green crystals here. So those give us a clue that they might be rich in magnesium and iron, silicate oxides. And that is really the bulk of what we can tell from the sample just by looking at this. But we can deduce a lot from that. If we compare images of these samples and the descriptions with other meteorites that have been found and classified, we can make a preliminary conclusion that these are fragments of an HED meteorite. So, sorry, my pointer went away. So, HED stands for howardite, eucrite, diogenite. Those are three different meteorite types that are associated. They're achondrites. And the HED meteorites come from a differentiated parent body. Now, what that means is that the parent body in space underwent melting. So let's say, for example, simplistically, you start with a very primitive rock like a chondrite, and you then melt that rock. That asteroid will start differentiating into different layers. Basically, you'll have magma or lava, or a magma ocean that will separate into layers. And it's very important because old meteorites like this must have formed very early in the history of the solar system to have melted. And we suspect they may have incorporated the short-lived nuclide aluminum-26. So this is just a schematic representation of what a differentiated body would look like. So you're basically taking a primitive body, you're melting it because of the heat generated by the short-lived nuclides. And then in this pool of magma, basically, there are some crystals and minerals that will crystallize first thermodynamically, and they will basically sink towards the center. And some of the later crystallized minerals will form shells higher up in the crust of the minor body. And you can even have volcanism on these bodies. So think of these layers as having crystallized from pools of lava. That's a good way to think of it. So the HEDs, if we look at the D, that stands for diogenite. And those represent shallow crustal or upper mantle cumulates that are rich in magnesium iron minerals, for example, those green crystals you saw. So on the little schematic there at the top right, that would be, say, represented by the second layer from the top down, perhaps, the greenish layer below the light layer. The eucrites would be surface lavas and or shallow magma, and they're rich in calcium minerals. So there's a compositional difference between these meteorites that we can pick up through further scientific analysis, and they would represent, they would be on the surface of the minor body. And then the Howardites, they represent regolith breccias. So they are mixtures of eucrites and diogenites that are produced by impact processes on the minor body surface. So as you're impacting and creating craters, you're mixing things up. And so excavating deep craters and mixing things, so you mix the eucrites and the diogenites and keep them on the surface. So these are really messy rocks. They're breccias. They're mixtures of all kinds of components of things that have been busted up. So it's important to note that while the HEDs as a group are relatively common on Earth, the Howardites and diogenites are among the rarest of observed falls. So we suspect that this meteorite that we have might be a Howardite or diogenite, but really these rocks are very tricky, and it's only when you get down to the microscopic scale that you can be definitive about them. So I say that with reservation. Now, another cool thing about the HEDs is that many decades ago, they were spectroscopically linked through visible and infrared spectra observations of rocks in the laboratory and in space. They were linked to the asteroid 4 Vesta. So HED meteorites have similar compositional optical spectra to an asteroid in space. So if you think about that, that's quite incredible that you can have a piece of rock in the lab, you can measure it, and then you can telescopically measure something in space amongst all the bodies in space and say, hey, these two things are remarkably similar. So for a long time, the scientific community has suspected that the HEDs come from the asteroid Vesta. So that is an image of Vesta. So it's the second largest asteroid, I believe. It's about 530 kilometers across. It resides in the main asteroid belt, which is about 2 to 3 astronomical units out in the solar system. And you can see a body like this, it's seen a lot of impact activity. So I was referring to the Howardites. Well, this is how these things form. There's lots of deep excavated craters. One of the deepest excavated crater is in the south, and it is believed that the source of the HED meteorites that we find on Earth actually comes from a big crater, perhaps like in the south. So all of this, including this image, courtesy of a very convenient NASA space mission to the asteroid 4 Vesta, and this mission is called Dawn. I believe at the moment it's at Ceres. I speak under correction, but Dawn visited 4 Vesta for several years, 2011 to 2018, after I think maybe a long journey in space. I think it was in space 4 years on its way to Vesta, then it got there. And it basically confirmed the long-held hypothesis that the HEDs are geochemically related to that asteroid. It is dynamically difficult to get HED meteorites off Vesta itself. However, there are other asteroids that are related to Vesta called the Vestoids or Vestoid family, and it is believed that they represent material that's been excavated from these deep craters on Vesta, and they lie closer to dynamically unstable regions in the asteroid belt, from which some near-Earth objects originate. So basically some of these asteroids are actually kicked out of the asteroid belt essentially, and they have an orbit that intersects with other planets in the Earth. So it is believed that the HEDs come from the Vestoid family of asteroids. So we are proposing the meteorite name Gqeberha. Sorry, my mouth is a little dry, I didn't get that click right. Gqeberha. That is the new place name of former Kirkwood in the Eastern Cape Province. We say it's proposed because we still have to classify the meteorite and then present the classification and the name suggestion to the Meteoritical Society's Nomenclature Committee. And, you know, I want to reiterate that really, you know, again, we've only had this meteorite a few days, you know, so there's a lot more science to come. So stay tuned. And my colleagues are now going to show you the meteorites. We're going to take them out of the desiccator where they're protected from moisture. And we are going to lay them out on the table. Please don't touch them. We're going to take a bit of time to unpack them, so please be patient. And then after that, we are going to turn over to my colleague to describe some of the further science that's going to come.
couple of minutes.
Would it help if I put it down on the foil?
Please.
Yeah.
Everybody will be able to
think we
take
can-
photos afterwards.
We can
Carry
continue
on,
and
and then
let us finish and then
we can finish, and this will be out, so everyone can take photos afterwards.
All right. Everybody will have an opportunity to look at it from close just now. And for now, I'd like to introduce Dr. Leo Witwatersrand, who will explain to us some of the science that we will be done on these samples and what it's going to tell us.
So now that the excitement has decreased a little bit, the sample will remain out, and everybody will be able to get a photo, a nice clear photo during the interview stage. So I'm going to take over after Dr. van der Kerk, and I'm going to speak about, or rather just summarize a whole lot of information that we've been presented here today, and then where we're going to go from here onwards. So, in brief, in a summary, how did we get here and where we're going to go? So, as Professor Gibson and Dr. van der Kerk have described, in the beginning there was cosmic dust, meteoroids, other planetary material, all circling as the solar system was forming. They started to clump together, agglomerate, and form bigger and bigger bodies. Some of these bodies got so large that melting was possible, and you started to develop things that have crust, core, and mantle, so differentiated bodies. And as was previously shown, this is what some of them look like today. So this is 4 Vesta, one of the largest asteroids, and is found in the asteroid belt. And meteorites that come from these type of bodies are called Vestan or Vestoids or HEDs. So from this big rock in space, how does it come to Earth? Well, as previously alluded to, something else hits it, causes an impact, and then stuff gets flown around. Sometimes, if we're very lucky, one of those pieces will make its way onto Earth. And that's where we find ourselves. So that's what happens in space, but how we see it is something like this, which is a lovely bolide, and why we are all here today. And what's just been revealed, we have some, which is very uncommon, as you've heard. A lot of the stuff gets lost to the ocean, a lot of the stuff falls into places where people don't see it. So having a sample, especially something with a story of as it fell, it was picked up, is incredibly rare and very, very exciting, both for the South African people, international community, international scientists, and South African heritage. So we've caught the car. Now what? So it's very simple. Dion has alluded to what we've done so far. We've done the macroscopic, or the large type of identification of minerals, looking at textures, the color of the sample, any of fractures, grain sizes, stuff like that, stuff that we can record and describe from the sample, the hand specimen that we have. Then we've weighed the sample, so we've got its mass. We can then do its density, and we do magnetic susceptibility. These are all physical properties of the sample, and we do this on as much of the material as we can get our hands on. After which, we have to make a thin section. So the 2 pieces of glass on the right-hand side. A little bit of material is consumed to make these very, very, very thin pieces of rock. They're sliced so thin that light can shine through them. And we use that on an optical microscope in order to identify minerals, look at shock, look at any alteration that has occurred on the sample. And this is an example on the bottom left of a chondrule in one of these thin sections that Roger has spoken about. So we do all of this in the beginning to get a firm understanding of the mineralogy, to get an understanding of what we're looking at. After which, seems to not have a photo there, but it's okay. We look at the chemistry or the geochemistry of these samples. We'll move from optical light, so using visible light to look at the sample, to something like a scanning electron microscope, which uses electrons to look at the sample. This is used to obtain chemical compositions of minerals. We can use the scanning electron microscope, or SEM, to get modal abundances, so how much of different minerals are in the sample, and map the thin section for future analysis. So to the right of the photo is a map of a sample thin section created by one of these instruments. After which, we'll use something like an electron microprobe, which is microscopic in situ, so in place analysis of minerals. We can get chemical compositions which are vital for us to classify this rock effectively and accurately. After which, we can also do isotopic analysis. In this case, oxygen isotopes are very vital and very useful for us to fingerprint where in the solar system this rock may have originated from. So, taking all this information, we need to officially classify this rock as a meteorite. And how we do that is we compile all the data that we've collected, so the descriptions, the physical properties, any chemical compositional data that we have, as well as the mineralogy. We put that all together and we combine it and we send it through to the Meteoritical Society, to which they vet and review our data, and if they agree with our proposed name and our proposed classification of the rock, it's certified, and then it becomes an official meteorite in the database of meteorites. That Gibson has said sounds like a lot, but in reality, very, very little amount of material exists. So after we've gotten the formalities out the way of classification, we can then do lots of other things. We can throw the kitchen sink at stuff like this. But it all depends on what the chemistry shows us and what we actually have available to work with. So stuff that we can do is we can use other type of isotopes to start to understand how these vestoid bodies or asteroidal bodies have formed, maybe the ages of the formation. We can use stable isotopes, again, to fingerprint where in the solar system, which asteroids or other bodies these meteorites come from. But not only about the parent body itself, we're also able to tell things about the time it is spent in space. So between its parent body and landing on Earth. We can use noble gases, and don't worry about the big names, but the other cosmogenic radionuclides. Essentially what they're looking at is how long it was exposed to space and the radiation in space. And we can also get approximate size estimates of what the meteoroid was before impact on Earth. So we can refine, as we already have, from car to motorbike to an actual proper estimate of what the meteoroid body was before it impacted Earth. But this all depends on what we find in our initial analyses, and that will guide us on our way forward. So that's a summary of how it's come to us and where we plan on going. So watch this space, and we hope to be able to update you as we get more information.
All right. Then you welcome back Professor Gibson for a little bit more presentation and a Q&A session after that, right?
Thank you. So I said I would bookend it, and so here I am. It's coming to the end. Firstly, we've just spoken about how busy we've been. I think we're probably averaging 3-4 hours sleep a night most of the time. People are driving large distances. We're running around. We're trying to catch people when they can talk to us and collect information. We're trying to do the science as well. But none of this would have been possible if there weren't a whole lot of other people who are getting very little sleep. And that includes the media teams from the 3 universities. So thank you to Prim, to Christelle and Sharona for getting everyone motivated and working really hard to make the event happen, to get the press releases out and so on. Particularly to Skulk, who I think really needs more sleep, because he's been working on this literally from when I think I phoned him on Sunday evening to say we need to get a press release out. So thank you for that. Also, thanks to the Eastern Cape Provincial Heritage Resources Agency for reacting so quickly. As we've said, we don't tend to move very fast in the geosciences world, but when it comes to heritage, you have to, and we need the permission of the Heritage Resources Agency to do that. So thanks so much for all your activity and bringing the team together and helping us with that. Also our support staff at our various universities and departments, who not only have helped us deal with the emergency, getting bookings of vehicles, etc., but actually they're going to become important in the time to come with the processing of the samples. The other thing is to thank Professor Chentu for hosting us and agreeing to host us. Unfortunately, Dr. Mahed couldn't be here, but thank you to Dr. Tenelia for standing in for him and chairing. And then the unseen people, the astronomers, Peter Hurst particularly, and Tim Cooper, as well as Daniel Kunama, who are really behind the scenes doing all the hard maths while we show you the rocks. Thanks to them. But particularly what the team wants to say is thanks so much to the people of the region and other regions who have been so good about sharing. And the online, this is our first online event. We had a little bit of a one in 2018, but it ended up in Botswana. But this is really showing what we can do if people are alert, aware, informed, and start to communicate. So thanks for that. And among those, the superstars. Sorry, it's quite something to see. Elise, for what you've done, for being so alert. And to the team from Cape Point, the team. It was definitely a team effort. The sharp eyes of Stephen, the amazing reflexes of Zoe, the analysis of MCA, as you put together that light show and that sound show that actually helped us to know what we were dealing with. And again, we're asking if people can continue to contribute. If you've seen something, just be honest about what you saw. It's not about being impressive or anything. It's just the honest opinions that we actually get to see. So that's my formalities out the way, and it's my job then to put it all together for you. It is only nearly 218 and a half hours since this event happened. It's phenomenal what we managed to achieve in this age of social media. Initial social media reports were confused and varied. It was a gas explosion, a nuclear explosion, an airplane crash, space junk, landslide, rockfall, earthquake, and of course the aliens featured very prominently in the J Bay area. So thank goodness for that indomitable South African spirit. But some were spot on. Some immediately, when Jessica posted and said, I think this might be a meteorite based on Elise's report, and people came in, and quite a few people were saying, yeah, it looks like it. Better get it to the heritage authorities. So we're informed. So let's put it all together then as a wrap-up. So we're going to break it up essentially into phase one, the visual side of it, what we call the luminous flight stage. And what we see here is this little sketch of what a typical bolide event should look like.
So somewhere at about just before 8:51 a.m., this object, which has been in space for tens, millions, hundreds of millions of years, coming from the dawn of our solar system, encountered Earth's atmosphere. And as it did so, it came in over the coastline, moving in an east-northeast to northeast direction, traveling at 20 kilometers or so per second. And it crossed the coastline somewhere between Gqeberha and George. The object itself was probably closer to 1 meter than 1.5 meters, based on the spectroscopic analysis that Tim is computing. We're hoping it's bigger. We geologists always hope that the rocks are bigger. Let's see. Maybe we'll get to our bubble car size at least. As it penetrated deeper into the atmosphere, the denser atmosphere caused more friction, so it starts to glow and ultimately melt as it heats up. And it starts to lose mass, and that's the tail of light that you can see behind it, the hot particles being pulled off it by this incredible speed, and it reduces its volume. The supersonic speed, of course, is creating a shock wave, a Mach wave, a sonic boom that's passing out. But in fact, the meteorite is moving the object is moving so fast, it's outstripping the sound wave at this point. So the boom is lagging behind already. And then at about 38 kilometers altitude, it meets its match. The atmosphere is too dense, or the fracturing within the object is too large. Gases are getting in from the atmosphere under this incredible pressure, and it literally heats, it's hot, so it explodes. Stephen notices that. Zoe reaches for her camera and records the final phases of the luminous flight, which her metadata then give us the actual time of the final end. So probably 5 to 10 seconds before that is that whole history, before Zoe starts to record it. And then, of course, after that, we enter the dark flight phase. So everyone thinks, wow, those were lights. Well, was there any smoke? No, let's get on with our lives. And 3 or 4 or 5 minutes later, there's this massive rumble of thunder, maybe accompanied by massive sonic booms, windows rattle, the ground shakes, doors rattle, and literally people can feel the vibrations through their feet, as MCA did on that sand dune as they were looking at it. And this is happening at the same time, the remaining particles, whatever's left, we hope it is more than this, but we have to find it. It should be more than that, but can we find it? And those particles are drifting down, initially on the flight path, straight line, and then they start to slowly feel the force of Earth's gravity, and they start to droop down on a parabolic curve. And there's a lot of maths that will go into calculating then where they actually end up. But they spread out. They don't all land in a lump. And by about 9 o'clock, so less than 9 minutes later, all is quiet again, except for that sound wave that's traveling all the way through the upper atmosphere as infrasound, heading to these nuclear test ban treaty stations like the one near Boshoff, where they will record the event and where scientists will then be able to detect it. So let's just put it all into perspective then. Is it an unusual event? Yes and no. The event is the 20th that is recorded on the database for this year, so it's little under one a week is occurring, and you can see them. And in fact, ours is one of the smallest of 2024, so we didn't quite make the top 3. But it still released 92 tons of energy, as light and as sound energy and explosive energy. It's one of only 3 bolides that have been reported over South Africa in recent times, but probably some of our other falls, our other 21 falls, have actually been associated with bolides. And the point is that the others, including the one in 2009 that we saw in Gauteng, were much, much larger. And that gives us pause for thought. We know that the meteorite appears to be a relatively rare HED type, achondrite breccia. If we find more pieces, we might find different types of rock within that, because it's a mishmash. So we hope to find more. And so to wrap up then, we've seen that there's an event that was much, much larger, 18,000 tons of TNT as opposed to 92, so many times more, that occurred over the Limpopo region and southern Zimbabwe and Botswana in 2009. But that's not the end of the story, because just a little over 11 years ago, in February of 2013, over the Chelyabinsk region in Russia, there was a 17 to 20 meter asteroid that came in as a bolide. It generated 440 kilotons of energy, which is about 20 times larger than the nuclear weapon that was used on Hiroshima at the end of the Second World War. It destroyed over 100,000 square meters of glass in 6 cities. That's the blast wave. So be thankful that the windows only rattled this time. Caused over 500 million rands worth of damage, and nearly 1,500 people were injured, mostly by flying glass as the windows blew in, but others by broken limbs falling on the ice because of the force of the air wave knocking them over, and even UV burns caused by the fact that the bolide was 30 times brighter than the sun, the energy released. So, to bring us all back then, what if? Could it happen again? What if? Well, it's happening all the time. Here's an example. Note the posts from the Western Cape only 5 years ago now. There's a bolide in daytime. It was spotted. It was on the news. Chelyabinsk, of course, was a disaster. So that bolide was about the same size. Well, it was about 10 times larger than the one that happened last week. Chelyabinsk, of course, was massive. But Chelyabinsk is only the middle part of a spectrum, because sitting 40 kilometers north of Pretoria is the Twying meteor crater. That is a 1 kilometer wide crater that probably was a 10 megaton explosion. If that crater, it happened about 220,000 years ago. And at that time, we know from the cradle of humankind that we have species like Homo naledi walking around. I'll probably get into trouble for saying this on international media, but Homo naledi must have witnessed the largest meteorite event that has possibly been hit the Earth since the dawn of our species. And yet that pales into insignificance to the Vredefort Dome near Parys and Vredefort in the Free State, which is the largest meteorite impact scar we have. So, to wrap it up, thank goodness our atmosphere protected us. This wasn't a particularly big event, but it was big enough to cause significant disturbance. It is a taste of what is possible when these rocks come in. We are, as a community of scientists, working to understand not only the rocks and their history and our origins in the solar system, but we're looking to understand the threat that these things pose to us, because they pose a continuous threat. 100 to 200 tons a day is coming in. And at the moment, there is a global network of cameras monitoring this. South Africa is part of that. There is a global network of telescopes trying to find these objects in space. There are millions of them. We are nowhere near being able to detect 1 or 2 or 3 meter-sized objects with any regularity. We don't even get the 100 meter diameter objects yet. But there is an effort to actually find a way to protect us against this. And the information that we are presented with here, the observations, the eyewitness reports, and the scientific calibration of those reports is an invaluable tool that will be read by scientists around the world as we continue to try and understand these phenomena and our way forward within them. So thank you very much for attending, and thank you for listening to us, and thank you to everyone for participating. Nicholas, I'm supposed to kind of sit here and see if there's questions and answers, but I'd like the team to come up and sit, and we can just see what you do. I don't know what the time frame is, how long we've got. Prim? Is Prim around? 10 minutes, okay. So, I don't know if anyone's monitoring international or not. So, questions? Do we have to have a